So now we shall quickly go through the commercial system, because so far we are representing this system in the form of schematic diagram, but the commercial systems, they do not look like those blocks which we have seen. And also those commercial vapor absorption refrigeration systems, those can be classified as single stage or single effect system, or they can also be classified as multi-stage or multi-effect system. The system which we have studied so far in this chapter, those were single stage because there were only two pressures. One was evaporator and absorber pressure. Other was condenser and generator pressure. So there were two pressure levels, 1 and 2. That is low and that is high. So just like in vapor compression systems, we call it single stage system. Similarly here in vapor absorption system, we call them single effect or single stage. Multi-stage or multi-effect system means when we have more than two pressure levels. So we shall see it in coming slides, right? Single stage or single effect systems, you already know there is only, so as I explained, there is condenser generator pressure and the other one is evaporator and absorber pressure. These single stage systems can be either in commercially available systems. Those could be either twin drum type or single drum type. So let's see what are those. So here you see single stage, but twin drum. Twin drum, as you see here, there are two drums. So those are made in drum shape or cylindrical shape. So this is drum 2, this is drum 1. So here in drum 1, we have absorber and evaporator. Both are at same pressure. And for water lithium bromide system, because so far we are discussing water lithium bromide system, here pressure is very low because we are making this water to evaporate in the range of 1 to maybe 5 degrees Celsius, because below this water will freeze, so water cannot be used temperature below 1 or below 0. So this is normally the temperature range and at which water is to be boiled. And absorber is also almost at the same pressure. So what is that pressure? That is P set corresponding to this one, and that is very low because when we make this water to boil at such low temperature, so pressure is normally very low, less than 1 bar, around about in the range of 0.07 or in this range bars. So you can see it's a very, very low pressure compared to atmospheric. So this is the pressure in the evaporator, which is equal to absorbed pressure. Similarly, generator and condenser, they are combined in one drum, right? And here pressure is again low because here we are condensing this water in the range of 30 to 50 degrees Celsius, depending upon the coolant or ambient or surrounding air temperature. So at this temperature, when water is to be condensed, again pressure is very low, about 0.07, right, in this range. Here it is 0.007 in the evaporator. In the condenser and generator, it is a little higher, but still compared to 1 bar, it is still very small. So it means the entire system, both drums, they are operating under vacuum pressure. So this is the major challenge in these systems because we have to maintain low pressure, much lower than this atmospheric pressure, normal atmospheric pressure. Only then this system can operate. So it means inside this system, we have very low pressure in this range, and outside is very high, 1 bar. So there is always a possibility of air leakage into the system. wherever you have weak joint, right, welded joint, there the air can leak into the system. So once air is leaked into the system, these pressures will disturb, and the refrigeration process will also disturb. Right, so that is the major issue with these systems, because those have to be operated at very low pressures. And also in these commercial systems, in the evaporator, for example, here you see the water is separate. The refrigerant is being separate over that tube. And in that tube, another chilled water is flowing to take and to give up its heat to this fluid. So, so a spray system is used in these systems. So what is the advantage? Because by spraying water in the evaporator section, it will boil more quickly, because by spraying the water in this form, the surface area of the water is increased, and more efficient will be the heat transfer in this section. Okay. So here, for example, chilled water is entering is at around 12 degrees Celsius. Here water is separate, this which is the refrigerant, at around temperature of 4. So there will be a heat transfer from this 12 degrees Celsius to 4 degrees Celsius. So its temperature will drop to about maybe 5 or 6 degrees Celsius. And here is our cooling load where this water is sent, this chilled water. Right. Same is here in the absorber, this strong solution, which is coming from the generator, right? In the absorber, that is also separate due to the same reason, because by spraying this solution, now it will absorb whatever water vapor is present here more efficiently, because the surface area of this strong solution surface area will increase when we spray it. So that will be helpful in good absorption of this water, which is evaporated here. So in these commercial systems, this spray system is normally used in both absorber and generator. And this system is normally used to produce chilled water. They are not directly cooling the room or space. They are used to cool the chilled water. Then this chilled water is sent to the room, right? Into the room. And there is another fan coil units, which we see in normal air conditioning systems, a fan coil unit. So this water goes into the room and comes back. So it's a closed loop. Okay. So the rest of the procedure is hopefully clear. You know what is the function of that heat exchanger, and what is happening in the generator and condenser. Here you can see in the generator, we are supplying a hot source of heat. It could be a steam, which is generated in a boiler. So maybe here we have a boiler where steam is generated, and this steam is sent to the generator to generate refrigerant, pure refrigerant. So there's a strong solution goes back. So, and this refrigerant gets condensed here. So in the condenser, you have a cooling source, which is another cooling water, right? Which is shown here. This is the cooling water coming from the cooling tower. First, it goes into the absorber. And then after picking this heat of absorption, then it goes into the condenser to absorb this heat also, because this here temperature is high, here temperature is low. So this cooling water first absorbs heat from this low temperature absorption system, and then it goes into the condenser where temperature is high, but still the temperature of this water is lower than condenser, or lower than this water which is being evaporated in the generator. And then it goes into the cooling tower again. So maybe I can show a cooling tower here. And in the cooling tower, you already know from chapter 4, there is air flowing, and this heat is transferred to the ambient air. Okay, so these refrigeration systems, these absorption refrigeration systems, those are normally available from small capacity of around 3 ton up to about 700 or maybe 1,000 tons. Those are available commercially, but not as common as vapor compression system, but still there are some manufacturers around the world which manufacture these systems in this range. Right. So this system which we have discussed, this is called single stage because there are only two pressure levels. One is evaporator, other is condenser and generator. So here we have evaporator and absorber, and twin drum because there are two separate drums. But in practice, we also have single drum systems. So you just go through this theory by yourself. It's not that difficult. This is just the functioning of the entire system, which we have already discussed. Here you see another version of commercial system, commercially available water lithium bromide system. It is still single stage, but single drum. All the components are in one single drum. So, but here, because we have two different pressures in that drum, so here is that diaphragm, which is a material which is separating these two portions, because here we have generator and condenser at same pressure and high pressure. And here we have evaporator and absorber pressure, which is some low pressure. But all of it is inside one single drum. And this heat exchanger is shown separately. And here is that cooling water from the cooling tower. A connection is provided for this cooling water. Similarly, a connection is provided for this chilled water collection. Okay. And another cooling tower, cooling water, which is taking heat from the absorber section. So the same system, but everything is in one single drum. Okay. So far, any question? Okay. So here we see still water lithium bromide system, but now it's a two-stage. Two-stage means here we have more than two pressure levels. So as you see in this figure, now we have more than one generator condenser combination. This is one, this is another generator combination. And this is same absorber and evaporator, okay, at some low pressure. But now you have two high pressure generator condenser combination. That is the highest pressure generator and condenser. That is, you can say, intermediate between this and this, intermediate generator and condenser. So these are called multi-effect systems, where a series of generators at different higher pressures are available. So heat is actually supplied to the highest pressure generator. So the external source of heat is supplied here only. Okay, here is the heat supplied at the highest pressure and at the highest temperature. This lower generator and condenser, they are at low pressure, lower than this one. So let me call it intermediate temperature and pressure. And this is the lowest temperature and pressure at which absorber and evaporator are operating. Okay, so we can have two-stage, we can have three-stage lithium bromide water systems. So now let's see the functioning. So here we are supplying heat at the highest temperature to this high pressure generator. So what happens here, whatever water is generated here, or refrigerant which is generated, now it condenses, but the heat of condensation is actually supplied to this low temperature evaporator, low temperature generator. This this water vapor which is generated, it is getting condensed here by rejecting its heat to this low temperature generator. For example, here we are generating this water vapor at around 150 degrees Celsius. So here this same water is getting condensed by rejecting its heat at such high temperature to this generator, where we are generating water at a lower temperature, for example, 80 degrees Celsius. So here we have this temperature difference available, which can be utilized to generate some water vapor from the low stage generator. And then after condensation in the high temperature or high pressure condenser, this liquid water is sent to this low pressure condenser. And here you see this expansion valve where pressure is reduced and temperature also gets reduced. So this all water is getting collected in that condenser. Okay, in the low stage condenser. For high stage condenser, we are not supplying any external cooling water. This high stage condenser is actually rejecting its heat to this low temperature generator. Okay. So it means we are generating refrigerant not only in this generator, but also we are generating refrigerant in this low temperature or intermediate pressure generator. So some refrigerant is generated here and some refrigerant is generated here. So overall, we can generate more mass flow rate, more mass of refrigerant, pure refrigerant, compared to single stage system. So it means those here, the capacity can be increased. And this here in this system, this heat which we have supplied in the generator, that is used more efficiently, not only to generate some refrigerant here, but also using the same heat to generate refrigerant here. So here heat input is more efficiently utilized. So such systems compared to single stage system, they can attain higher COPs, because single stage systems, their COP is in the range of, for single stage, is in the range of 0.7. But by utilizing two-stage or three-stage systems, we can achieve COPs greater than 1. Okay. So here again, if something is not clear, for example, here from the absorber, here that is the weak solution which is collected at the bottom of that absorber. Now it is pumped to the highest generator, and that is the strong solution coming from the highest generator. And here is that heat exchange between this strong solution and that weak solution. And this strong solution is now going into the low stage generator, where again and there is an expansion valve because it is at high pressure, this is at low pressure. And then this strong solution, some more refrigerant is evaporated, then this strong solution is going to the absorber section, and in between this low and or intermediate generator and low pressure absorber, there is another heat exchanger. So there are two heat exchangers. Okay, so that's how this system is working. In triple stage system, we can have another generator and condenser at very high temperature. So maybe at 200 degrees Celsius, we can have another generator and absorber, right? So we can have triple effect. Water lithium bromide system. So here the basic working of that system is mentioned. If anything is not clear, then you can ask. This is a pump. This is expansion valves to reduce the pressure from high pressure to intermediate, then from intermediate to low pressure. Okay. The rest of the working principle is same, but the main advantage is there. Here we are supplying heat at a higher temperature than single stage system. So if you remember when we developed that COP correlation of a uh, Carnot vapor absorption system, it was a function of TG, the generated temperature. Higher is the generated temperature, higher will be the COP of that Carnot system. That is not only for that reversible refrigeration, but also for the actual system. That is the case. Higher is the TG, higher will be the COP. Okay. Because we can increase the amount of refrigerant. We can generate more refrigerant vapor, which leads to higher COPs. Okay. The same system, the double stage, is shown here on this pressure versus temperature diagram. So here again, if we start from the evaporator, which is at the lowest pressure, lowest temperature. Now at the same pressure, it goes into the absorber. So temperature increase, this is the T of absorption. Now this weak solution is pumped through those heat exchangers, and now its temperature is increasing because it is exchanging heat with this strong solution coming back from the generators. So here some temperature is increased in this solution heat exchanger, then some more temperature is increased in the second solution heat exchanger with this solution coming from generator. And what is that solution? It's a strong solution. And this solution coming from absorber and going towards generator is weak solution. And in the generator, we are supplying heat at the highest temperature. Here you see the highest temperature heat is supplied in generator 2. So in generator 2, whatever refrigerant is generated, it is condensed. But here the temperature of this condenser is still higher, and that is used to generate some more refrigerant in this low temperature generator. And from this generator, some more refrigerant is generated. So here some refrigerant is generated, here some refrigerant is generated, and the heat of condensation is used here. So then whatever liquid water we receive, it is throttled to low pressure condenser. So there are two condensers. And this heat is again rejected to the normal ambient. But here the heat of condensation of condenser 2 is rejected to low temperature generator. Okay, this is generator 1. In the generator 1, because we need temperature at low temperature, it is normally required. So here we can use normal solar collector. For example, there are many types of solar collector: flat plate, evacuated tube solar collectors, evacuated tube solar collector, flat plate solar collector, or concentrator type solar collectors. So those because they can give us the simplest, but they can give temperature in the range of 60 to 80. But evacuated type solar collectors, they can give us temperature around 80 to 150. And these concentrator type solar collectors, they can give temperatures in the range of 200 to 300 degrees Celsius. So for this low temperature range, we can use these normal solar collectors, low cost solar collectors, to derive this generator 1. The heat can be supplied here. And would this concentrated type solar collectors, which can produce such high temperature fluid, that can be used here in generator 2. So here is just a general schematic telling us, explaining us the overall working of that multi-effect absorption system, which type that so far we are discussing water lithium bromide system. Okay. Any question? Yeah, there is no question. Then the next last part of that chapter, of course, we cannot cover its mathematical part, only the description of that system. The second one, which is water and lithium, sorry, water ammonia pair. Okay. That is vapor absorption refrigeration system, which is based on water ammonia pair. In these systems, the refrigerant is ammonia, absorbent is water. These systems can be used for both air conditioning applications and also for refrigeration applications, because here the refrigerant is ammonia, and ammonia does not freeze at temperatures 0 or less than 0. Okay, so the freezing point of ammonia is very low, so that's why we can use these systems for freezing applications. These systems are much more complex compared to water lithium bromide system. And one of the major issue with these systems here, the boiling point difference between these two, refrigerant and absorber, is very low. It's only 133, but in case of water lithium bromide system, this temperature difference was around 200 degrees Celsius or more than 200 degrees Celsius. So here we have this issue that always some absorbent will evaporate with ammonia. Ammonia is the refrigerant, and this is the absorbent. So that's why here we have to introduce some other components to remove water fully from ammonia before it goes into the condenser. Okay. And also there is a issue with ammonia. Ammonia, you cannot use it with copper or brass, which is the most commonly used material in refrigeration and air conditioning applications. All those evaporators and condensers normally which you see in our offices or in our homes, those are made up of copper or brass. But ammonia is not compatible with these materials. They start to react with these materials. So that's why in case of ammonia systems, the entire system is actually made up of steel. So copper cannot be used here. So we cannot take advantage of copper's highest thermal conductivity in this case. But there is an advantage compared to water lithium bromide system, because in water lithium bromide system, water was the refrigerant. That's why those have to be operated at very low pressure. High vacuum pressure we have to maintain. But in this case, for ammonia water systems, there is no such issue. Ammonia can be evaporated at normal ambient pressure or even higher than ambient pressure. So in these water ammonia systems, pressure is much higher than atmospheric. So there is no issue of air leaking into the system, because in these systems, pressures are higher than ambient pressure. And also, in these systems, there is no issue of crystallization, which was the problem here in water lithium bromide system. At certain temperatures and pressure or at certain concentration levels, lithium bromide may crystallize. So we always need to avoid that that condition. But here there is no such issue. In water ammonia system, there is no issue of crystallization. Okay. So there are some advantages, some disadvantages. Here we have another major disadvantage of ammonia. It is not only toxic, it is also flammable. That's why these systems need some special safety precautions. Okay. So yeah, these are some advantages and disadvantages. And here is the basic operation of the same water ammonia system. The basic system is shown here. The working is exactly same as water lithium bromide system. The only difference here is now absorber is water, and refrigerant is here is ammonia. And ammonia, we can evaporate ammonia in liquid form at such low temperatures, right? Without freezing. Okay. That is the major advantage. Okay. And here again in the absorber, we have to keep the low temperature to not lose the absorption efficiency, right? So here we'll have whatever ammonia is generated here, it will be absorbed by this water. Okay. And this strong solution is now just like in water. Lithium bromide system, it is pumped to the generator. Here we are supplying heat at a high temperature and high pressure. So the pure ammonia, ideally we want pure ammonia should be evaporated. Okay. So ideally pure ammonia should flow towards the condenser. Okay. And here ammonia is condensed and throttled and the cycle is repeated. Here whatever weak ammonia is left, that is sent back to the absorber using a throttling valve. So that is the basic operation of that vapor absorption system based on water ammonia. Okay, so I think everything is clear. There is nothing too difficult. It's exactly same. The overall working principle. Okay, it's very much similar. But there are two major drawbacks in these systems. The first one is the same as we had in water lithium bromide system, because this weak solution which is coming back from the generator, it is at high temperature, for example 85. Okay, so high temperature ammonia is entering into the absorber, and here we want low temperature, and similarly this low temperature absorber fluid is going towards or is flowing towards generator. So here, just like in water lithium bromide system, we can install a heat exchanger here. Okay, so that the temperature of this weak solution can be increased and the temperature of this strong solution which is coming back should be dropped. Okay. So this is the first drawback which we can eliminate using the same method or the same component which we used in water lithium bromide system. Use a heat exchanger between absorber and generator. The second drawback, which is specific to ammonia water system, is this one. What is this one here? Ideally, we want only ammonia should evaporate in the generator, but actually some water also generate because the boiling temperature of water and ammonia are not that far, right? So that's why water. And if some water is evaporated here, look, if some water is getting evaporated with ammonia, and here we are operating this evaporator at such low temperature, freezing temperature. So whatever water will come here with ammonia, once it will reach in this low temperature region, so whatever water will be there, it will freeze. So it will choke the whole circuit. So that's why we need to have, we need to make sure that no water should be evaporating with ammonia. But issue is that the boiling point difference between ammonia and water is not that big. And also water is very volatile substance. At every temperature, some of the water may be evaporating from its surface. Okay, it's not like lithium bromide, which is normally a salt. Right, so that is the major issue. For that issue to be resolved, this is what we discussed. We use two more components, that is called analyzer and rectifier. Okay. So this second drawback, this one, because water is evaporating with ammonia, and we want to eliminate whatever water is evaporated in the generator before it goes into the condenser. So for that, there are two more components installed, which are known as analyzer and rectifier. Okay, so one is analyzer, other is rectifier. Those are shown here in this diagram. So the entire system is same as before. So I will briefly explain in the next class what is the function of this rectifier and analyzer. The purpose is simple. We want to eliminate whatever water is evaporating inside this generator, and this water should be condensed back. Only ammonia, pure ammonia, should be flowing towards the condenser. So the working principle of these two are very simple. So I will explain in the next class, and then we shall start the next chapter. Okay, so I stop here. Okay, any question? Okay, so that's all for today. So we shall meet tomorrow or day after tomorrow, inshallah.